Hi everyone, I am Sam. Today we are going to talk about glaciation. Imagine yourself perched high above a sprawling city made of ice. The towers and spires below appear frozen in time, but if you stay long enough, days, months, even years, you'd notice that these gleaming structures are constantly shifting and flowing. They're not solid buildings at all, but rather slow, relentless rivers of ice pushing forward inch by inch, carving canyons, polishing bedrock, and shaping landscapes on a scale too large and gradual for the casual observer to witness. This is the world of glaciation, where massive glaciers act as geological sculptors, altering the face of our planet one frostbitten inch at a time. To fully appreciate how glaciers have influenced Earth's history, we need to look back at the people who first dared to question how enormous sheets of ice could once have stretched across places that now enjoy relatively mild climates. In the early days of modern geology, around the late 1700s, most thinkers found it difficult to imagine landscapes changing dramatically over long spans of time. The popular belief was that Earth's major features had always been the same. But occasionally, an inquisitive soul would stumble upon a curious sight: erratic boulders perched impossibly far from any likely source, or deep scratches gouged into the bedrock, and wonder if something beyond the ordinary had dragged, dropped, or scraped these features into place. One of those inquisitive souls was Swiss naturalist Louis Agassiz, who, in the 19th century, passionately argued that ice, on a continental scale, had once shaped the northern lands. Initially, many scientists dismissed his claims. The idea that huge glaciers had covered much of Europe, North America, and beyond seemed preposterous. Think of it like hearing, for the first time, that the Sahara Desert was once a sea. A staggering shift of imagination that flies in the face of what your eyes can see today. But gradually, the weight of evidence, moraine deposits, erratic rocks, deep scouring of valleys, became harder to ignore, and Agassiz's theory of a grand ice age began to gain traction. To understand how glaciers form, picture dropping scoops of fluffy snow into a transparent container. At first, the snow piles up, full of air pockets. But over time and under pressure, that light, crystalline fluff compresses into dense ice. On mountaintops or at polar latitudes where temperatures remain cold year-round, snow that survives the summer gradually transforms into firn, an intermediate stage, and then finally into glacier ice. Once a mass of ice becomes thick enough, usually at least 100 feet deep, it starts to flow downhill under its own weight. Imagine slowly pressing your hand against a lump of warm modeling clay. The clay deforms and oozes away from the pressure point, and glaciers do something surprisingly similar, only on a colossal scale. Glaciers have shaped human cultures almost as decisively as they've shaped landscapes. Early communities in mountainous regions had to learn to navigate icy passes and seasonal meltwater floods. In the Arctic, indigenous groups developed sleds, kayaks, and specialized clothing to contend with glacial and sea ice. Even today, millions of people rely on glacial melt for fresh water, from the Ganges River, fed by Himalayan glaciers, to South American communities downstream of the Andes. The ice ages, of which there have been several in Earth's deep history, also forced humans to migrate, adapt, and innovate, leaving marks on our myths, languages, and migrations. One key realization that advanced our understanding of glaciation is the concept of repeated ice ages. Earth wasn't glaciated just once. Several times over the last few million years, ice sheets advanced across large parts of the northern hemisphere, retreated, and then advanced again. Scientists came to understand these cycles by observing rocks on ocean floors, analyzing trapped bubbles of ancient air in polar ice cores, and studying the distribution of fossils. Think of it like detective work. Each new piece of evidence offered clues to the timing, extent, and drivers of these glacial episodes. In the early 20th century, Serbian mathematician Milutin Milankovitch added a major breakthrough to the story. He proposed that variations in Earth's orbit and tilt, often called Milankovitch cycles, periodically change how much sunlight different parts of the globe receive, influencing the onset and retreat of ice ages. It's akin to adjusting the brightness of a heat lamp on a patch of snow in your backyard. Sometimes the lamp's position and intensity are just right to cause melting, while other times the snow remains undisturbed. This theory helped explain the puzzle of why Earth's climate shifted between cooler, glaciated periods and warmer interglacial intervals. However, like any good mystery, glaciation wasn't solved by a single clue. Scientists still debate the interplay between greenhouse gases, ocean currents, and continental positions that either amplify or dampen those orbital shifts. Some researchers point to the arrangement of continents, like Antarctica's isolated position at the South Pole, as a critical factor that allowed thick, stable ice sheets to form. Others emphasize the role of carbon dioxide in shaping global temperatures. The debate continues, drawing in glaciologists, climatologists, geophysicists, chemists, and paleontologists, each bringing their own perspective and specialized techniques to piece together the grand puzzle. One challenge that glaciologists face today is investigating the hidden underbelly of these ice giants, the subglacial environment. Beneath some glaciers, meltwater flows in channels and lubricates the ice above, speeding its movement. Under others, the ice is frozen solid to the bedrock, slowing the glacier's march. Understanding these processes requires high-tech radar and satellite imaging, along with data from drilling projects that retrieve ice cores. If you've ever tried to figure out whether a rug is wrinkling on a slippery floor or stuck on rough carpet underneath, you have a small-scale analogy for the complexities that scientists confront when analyzing glacier motion. Controversies in glaciology often revolve around how quickly glaciers will respond to changes in climate. While we know global temperatures have risen, ice sheets in Greenland and Antarctica are responding at different rates. Mountain glaciers around the world are retreating, threatening water supplies for millions. Will parts of the West Antarctic ice sheet collapse within a century, raising sea levels by several feet? Or will the process take longer, buying coastal communities more time? Researchers publish papers with competing models, each one trying to refine assumptions about ice dynamics, ocean warming, and atmospheric feedbacks. These debates aren't a sign of a shaky science. Rather, they highlight just how complex and multifaceted the glacial system is. Scientists are building a clearer picture by challenging each other's ideas and testing them against real-world observations. Yet, for all the heated discussions among scientists, there's also a spirit of collaboration. International teams drill miles into polar ice to extract cylindrical cores, preserving snapshots of Earth's climate going back hundreds of thousands of years. At the surface, the freeze in Antarctica tests not just scientific resolve, but also human endurance and camaraderie. It's telling that many polar research stations emphasize communal meals, group problem-solving, and shared responsibilities, like carefully rationing resources or taking turns washing dishes. In these extreme environments, the human story of glaciology becomes as fascinating as the science itself. Researchers contend with 24-hour darkness in winter, howling winds, and the risks of frostbite and isolation, all in the name of uncovering Earth's frozen past and potential future. Despite centuries of study, glaciation still holds plenty of secrets. How quickly can massive ice sheets calve into the sea? What hidden lakes and microbial ecosystems exist beneath miles of Antarctic ice? How did ancient ice ages shape evolutionary paths for plants and animals? And perhaps the biggest question of all, how will ongoing climate change alter the balance of Earth's ice? And what will that mean for sea levels, weather patterns, and global ecology? Answering these questions requires a mix of cutting-edge technology and old-fashioned detective work. Satellites now measure the changing mass of ice sheets with astounding precision, while drones and autonomous underwater vehicles probe beneath floating ice shelves. Meanwhile, researchers pore over historic diaries, photographs, and sketches, sometimes centuries old, to see how glaciers have changed over human memory. It's a bit like mapping a family tree, where each piece of old correspondence helps fill in a gap in our ancestors' story. Perhaps the most important lesson we can glean from the study of glaciation is an appreciation for the slow yet powerful forces that shape our world. Glaciers move on timescales that defy daily human experience, but they can etch entire continents over tens of thousands of years. Their relentless presence reminds us that the planet is always in flux, even when our own lifespans are too brief to notice. And while glaciers often symbolize stoic stillness, they are anything but inert. They're busy sculpting valleys, storing fresh water, influencing ocean currents, and creating habitats for a host of specialized organisms. For those of us living in a world increasingly defined by rapid change, it can be oddly comforting to remember that these monumental rivers of ice are part of an ongoing cycle that stretches far beyond any single human generation. Glaciation is a story of transformation on a grand scale, a story we're still learning to read, decipher, and tell. Each new discovery about the planet's frozen realms holds the potential to reshape our understanding of Earth's past and guide us toward more informed decisions about its future. So the next time you find yourself in a snowy landscape, take a moment to imagine the slow, steady push of an ancient glacier carving mountains, stacking moraines, and dropping boulders miles from their original homes. That unhurried yet unstoppable flow is the heartbeat of a process that has left its signature across continents, shaped civilizations, and continues to challenge our scientific understanding. It's a reminder that, although we might see Earth as fixed beneath our feet, our planet is alive with hidden motion and ice-bound secrets, gently urging us to keep asking questions and seeking answers in this ever-evolving frozen saga. That's it for today, and I'll see you in the next episode.